The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
Good afternoon. So it's my pleasure to be here this afternoon and have a chance to talk to you about what I think is the world's greatest challenge at the moment, which is dealing with energy and trying to understand how we meet the dual challenge as we get out to 2050 and beyond of providing twice as much energy for the world and at the same time substantially reducing the carbon content of that energy. So I'd like to begin with just a couple of slides to make that framing point, that we look at a doubling of energy demand going out to mid-century, and at the same time we have a strong need to eliminate carbon from the system. So the first couple of slides I'll show come from coupled economic climate forecasting by a group at MIT known as the Joint Program on the Science and Policy of Global Change. This is a group that brings together economists, primarily from our business school, and climate scientists from our Earth, Atmospheric, and Planetary Sciences department to understand the coupling between different sectors of our economy, and I'm particularly interested in the energy pieces of those sectors and impacts on climate. The model I'll show is a very conservative model, call it a business as usual scenario, that's based on basically the 2009 Framework Convention at Copenhagen. And the assumption here in the slides I'll show, the assumption is that countries will follow the voluntary agreements they made at Copenhagen, but that there will be no new agreements. All right, so that's clearly conservative. There were some modifications at the Copenhagen meeting in 2010, but those are minor perturbations. Not factored in here the commitments that the Chinese made back in November to peak in 2030 in carbon emissions. The results will be shown by dividing the world into three course blocks. Those are developed countries, the US, Canada, the EU, Australia, New Zealand, Japan. Then other G20 countries, including Brazil, China, India, and so on, major, very rapidly growing economies. And then the third group are other developing countries. And so what I like to look at in these next couple of slides is what's the projected energy growth in those different parts of the world, and what's the impact of that on carbon emissions. So this is a look at the projected growth in energy demand. And what you'll see is that roughly from today or a little bit before today, 2010, the projection is that energy demand will grow to about twice what it is today. And that's driven by two factors that I think we're all familiar with. One of those is population growth. Population expected to grow past 10 billion as we get to mid-century and end-century. And secondly is the increasing standard of living of the people on the planet. As standard of living increases, so does energy use per person. And of course, that coupled with growing population is a huge driver on energy demand. The other thing to take away from this slide is how will we meet those energy demand growth expectations in a world where we don't do anything by way of a carbon price or cap and trade globally. And the result is that by mid-century, we'll have still about 80% of our energy supplied by hydrocarbons. Right? So coal, oil, natural gas, the main sources of energy. And these results you see in lots of studies on projected energy growth. BP's most recent study, for example, shows almost an equally divided energy picture in 2050, 27% each for coal, oil, and natural gas. Of course, that can change if we put a price on carbon. Another point in this slide, which I make in the numbers on the margin, is that there's a lot of fossil energy in the world, and we are not going to quit using fossil fuels because we run out, right? We're going to stop using fossil fuels because we run out of a place to put the carbon dioxide, right? And that's important to keep in mind. We need to think about how to get carbon out of this system. This is a look at how that energy demand growth breaks down into these three big sectors I talked about, three big blocks of countries. Interestingly, you'll note that in the developed countries, the graph on the far left, energy demand is essentially flat to slightly decreasing over the next 35 years or so out to mid-century. And so what you see is that as we follow the agreements for the Copenhagen Accord, we decrease gradually at first and then flatten out towards end of the first half of this century. The big growth around the world happens in the developing world. The other G20 is the big sector, so Brazil, China, India, Russia, and so on, is the big growth sector. And there you'll see that we go from their energy use, your energy use today, to essentially the total global energy use, but just in these other G20 countries by mid-century. And the predominant part of that growth comes in the fossil energy sector. And then on the far right, you'll see that the other developing countries also grow substantially, almost entirely, in fossil fuels, and that by mid-century, their total energy use is about the same as the developed world today. All right, so again, very substantial energy growth. Oops. So this slide looks at the greenhouse gas emissions, primarily CO2 emissions, globally as energy use grows, going out to mid-century. And what you'll notice is, first of all, the substantial greenhouse gas emissions growth. And secondly, if you look at the distribution by major group, you'll see that, like the energy demand, growth is flat to slightly decreasing in the developed world. The bulk of the growth happens in the other G20 countries, Brazil, China, India, and then the developing countries, other developing countries, contribute to significant growth in the gray bar at the top. So serious growth in energy demand, and at the same time, growth in carbon dioxide emissions and other greenhouse gases. So to meet reasonable climate targets, we're going to need to do that growth in energy plus get the carbon out of the system. And that's a challenge, I think, that demands a strong role for science, technology, and innovation. And that's what I'd like to talk about for the bulk of this presentation, is a look at a set of game-changing energy technologies from MIT that are helping us to address this dual challenge of growth plus elimination of carbon from the system. By any stretch of the imagination, energy research, technology development in energy is essential to our well-being. It helps us in three key ways. First, it helps us in economic growth. Second, it helps us in improved security. And third, it can help us with a better environment. Right? I can't think of a better way to illustrate that than the shale gas and shale oil revolutions in the U.S. This is a technology that goes way back. The earliest technology developments in this field I know of were just post-World War II. 1949 began work sponsored by the Department of Defense in the U.S. on 3D imaging technology that was not directed at shale gas, but it was directed at how to follow Soviet subs that were leaving the North Sea and entering the North Atlantic. So it was concerns about Cold War activity. Later, in the 90s, the Department of Energy in the U.S. Started substantial funding to look at fracking technologies and how could we understand how rock structures are fractured with hydraulic injections. How do you control that? How do you have control on exactly how the fracture patterns occur and where they're located. That plus horizontal drilling developments in the 90s and in the early 2000s led to the ability to produce these resources that before we were unable to tap. And the result in the U.S. has been an unparalleled expansion in the proven reserves of natural gas. We thought we were running out of gas in the U.S. Back in the 90s, and an explosion in oil production, such that the U.S. is now the world's largest producer of oil and gas combined, and interestingly has become the swing producer for oil globally, since shale oil can be produced in a very modular fashion. This has clearly had a big impact on economic growth in the U.S. The chemical industry is thriving and booming because of the natural gas liquids that go with shale gas production. Improved security because we now have a more diverse supply of the energy we use in the U.S. And you'll notice I associated security with diversity of supply and not with energy independence, which is a mistake that many people make, I believe. And thirdly, we have a better environmental footprint in the U.S. because of shale gas, driven by the low cost of gas, which has resulted in fuel switching in power production in many coal plants from coal to natural gas. U.S. emissions of CO2 are at levels we haven't seen since the 1990s. And there's hope that that can be amplified going forward with the Clean Power Plan Act or rule set from our Environmental Protection Agency. So major contributions from a research program that took many years, starting with some very basic research and moving through to applied technology and application to an interesting and important domain area. So I tell that story to make the point of the need for long-term sustained basic research in energy to make for a better future for all of us. I'm going to give a one-slide advertisement for the MIT Energy Initiative. This is the group that works to bring together expertise across the MIT campus to make major advances in energy technology. We were formed around late 2006, early 2007, with the idea of bringing scientists, engineers, business people, economists, political scientists, and architects and urban planners together to think about how we could transform the world's energy systems. We have gotten broad engagement across campus. Our faculty are very committed to making this a better world by using their own technology and science and business skills. So we've now got about 25 to 30% of the faculty at MIT who work with us on energy problems. So going from the science up to policy and applications. We're a very broadly focused initiative, so we look across energy from production technologies to conversion technologies to transmission, distribution, end-use applications, and associated environmental challenges. You can't look at energy without considering what it does to the environment. CO2 emissions, for example, or increasingly understanding the water energy nexus. We divide the research program at MIT in the Energy Initiative into a couple of broad categories. I'll emphasize the first two here. One of those is what we call innovation. And the idea there is based on the fact that our energy system, our global energy system, is a multi-trillion-dollar global enterprise. It doesn't change rapidly. The result is we'll be using the energy sources and energy technologies we have today for many years to come. Coal plants, for example, are built on the assumption they'll operate for 40 years or so. So a challenge for us is to learn how to use those technologies as efficiently and as environmentally responsibly as we can. And so that's what this innovation section is about, making the world better with technologies we have in use today. The second big area is what I call transformations. So these are the technologies for the future. These are the ones that will scale up to be the major energy producers mid-century and end of century. So things like solar energy, biomass to fuels, biomass to chemicals, wind energy, geothermal energy, long list of these. These are all technologies that are practiced today. They're technologies that by and large are not practiced at global energy scales. Right? So there's a lot we have to learn yet about how to make those cheaper and scalable to make those become an important part of the global energy system. So I'm going to tell some stories now about game-changing technologies developed at MIT in a number of different fields to illustrate how we're taking science and moving it into the marketplace to impact today's system and to develop for the future system of tomorrow. First example I'll go quickly over because Professor Gleason, in her talk earlier this afternoon, gave some examples of this technology. About 85% of the world's electricity is made in thermal power plants, right? Power plants that generate heat, produce steam, run that through a turbine, and at the end condense the steam back to water so it can be run back through the process again. This technology, which is developed jointly by Professor Gleason in chemical engineering and Professor Kripa Varanasi in mechanical engineering, develops a coating that can be put on the surface of the condenser, the last stage of this process to get water back for reprocessing. A surface coating that improves the heat transfer efficiency of the condenser by a factor of 7. Right? In most condensers today, you get what's called film condensation. So you develop a film of water that's been condensed on the surface of the condenser, and that severely degrades the transfer of heat from the moist air to the condenser surface. By putting on this coating they've developed using chemical vapor deposition technologies that Professor Gleason talked about this morning, they're able to force dropwise condensation and get this very improved heat transfer rate, thereby increasing the efficiency of the overall process. What's even more interesting about this technology is that it's a technology that can be used in retrofit applications. Most condensers, I think all condensers, run under vacuum or partial vacuum. That allows you to hook a CVD system up to it and do a deposition on existing condensers. So a technology that comes out of very basic research in Professor Gleason's lab, understanding how to do directed chemistry in vapor deposition processes, and Professor Varanasi's group in mechanical engineering, where he's developed very basic and clear understandings of how surfaces and surface properties can be modified for different applications. You don't always do power plant applications. Probably Kripa's most famous application is coating a ketchup bottle so that the ketchup falls out of the bottle and doesn't stick. You don't have to shake the bottle. Another example of an innovative technology, an innovation on today's systems, is a carbon capture technology. If we're going to continue to use fossil fuels well into mid-century and beyond, we're going to have a way to get the carbon dioxide out of the gas that comes out of the combustion system. Right? We know how to do that today. We often use, or typically use, an amine capture technology. We use an amine solution that the carbon dioxide is bubbled up through, and the amine absorbs the CO2. Problem is to recycle the amine, which you need to do for economic reasons, you have to heat it up, the amine carbon dioxide solution, you have to heat it up with steam from the power plant to make it let go of the carbon dioxide, capture the pure CO2 stream, and then recycle the amine. That costs money. It costs money for the steam that you're taking away from the power plant electricity operation. It costs money to do a replumbing and redesign of the steam power plant to get the steam over to the desorption column. What Professor Haddon has done is to discover an interesting electrochemical process in which he adds a third species to this system. I think copper ion is a favored way to do this, such that if he applies the right electric field to a mixture of amine, CO2, and copper ion, the amine solution, the amine prefers the copper ion to the CO2, and so it'll let go. Right? If he then reverses the field and recycles the amine prefers the CO2. Right? So you can get this absorption, desorption process to run by altering an electric field rather than by replumbing the process and by using a lot of the process steam that otherwise could be used to make electricity. So there's much less parasitic load on the process in this technology. A very promising technology. What I think this points out is the need for lots of innovative research on how to capture CO2 from various processes that use CO2 today. Another interesting innovative technology involving CO2 is work in Professor Angela Belcher's lab at MIT using genetic engineering on yeasts to make yeast that can take calcium ions or some other metal ion, capture CO2, and then mediate the chemistry to build up structures of the metal ion plus carbon dioxide, so carbonates, that have desirable material structures. And she's motivated by what nature does, for example, with an abalone shell, which is mostly about 98% calcium carbonate, but it's much, much stronger than a piece of chalk, and that's because the biology in that system has learned over millions and millions of years how to develop a nanostructure which can reinforce the properties. So she's working at doing that here and making building materials, so materials that could be used in large volume and take up large volumes of CO2 and get productive uses and a financial or economic value from the CO2. Another example of innovative work that has come out of the Energy Initiative at MIT is a desalination technology, which Professor Lienhardt will talk a lot more about in his presentation, in which one of our faculty, Professor Jeffrey Grossman, has developed a one-atom thick membrane from a graphene sheet. Graphene is carbon in a particular molecular structure that's one atom thick. He drills holes in this graphene sheet which let water pass through but block salt ions. By taking advantage of the fact that this graphene sheet is so thin, he can reduce pressure drops and thereby reduce the cost of desalination. An interesting observation here, which was recognized by the Smithsonian Institution, they recognize each year what they regard as the 5 most surprising science discoveries of the year. In 2012, when this was published, they recognized 5 science discoveries. One of those was the discovery of the Higgs boson. This is a multi-billion-dollar international experiment. One was the images that came back from the Mars rover. The Smithsonian said that's not a discovery, but it's really neat, so they gave it one of their 5. And one of the 5 was this project, which was not a multi-billion-dollar project. It was a $150,000 seed fund project from the MIT Energy Initiative. So really good value for the money. transformative technologies. Wind energy is one of the most cost-effective renewables today, but wind, like solar, suffers from the disadvantage that it's intermittent. And so a key technology for wind and solar will be storage. How do I store excess wind or energy when I don't need it and get it back when I do need it? This is work from a laboratory in mechanical engineering run by Professor Alex Slocum. He's probably one of the most out-of-box thinkers you will ever meet, so he fits really well with the title of the conference. His idea was to take, for offshore wind that's in deep enough water that you have to put the windmill or the wind turbine on a floating platform, much like you use in oil and gas production. You have to anchor that platform to the seafloor. So what he wants to use are large, hollow, heavy objects as anchors. And then when he has excess wind, he'll pump water out of this hollow object, big sphere, or more likely a large pipe. Pump water out of the pipe, and then when he has no wind, he'll let water flow back into the pipe through a turbine, and thereby produce electricity, actually very efficiently, because I can control the flow rate of the water to optimize the performance of the water turbine in this case. So very interesting technology that combines two different facets of the problem into a nice synergy. Another interesting technology, also out of Professor Slocum's lab, along with faculty in nuclear science and engineering, is what we call CS-PON, or Concentrated Solar Power on Demand. The idea here is based on a technology known as concentrated solar power. It's a solar thermal technology in which you focus direct normal solar radiation with mirrors onto some object, usually, that you heat up. And that hot object is used to heat water, to make steam, to make electricity in a traditional thermal power plant. In this version of the process, rather than focusing on a heat exchanger, which you might find on a tower, he focuses the light into a tank, and in the tank he has a full system of molten salt. Today it's a potassium nitrate, sodium nitrate mixture of salts. The beauty of that change is that I can go to much higher intensity of solar radiation into my absorber than I can on a tower up on a heat exchanger on top of a tower. The reason why I can go to much higher energy fluxes is that in the tank I absorb the energy over several meters of salt. If there's a fluctuation in the intensity of the solar radiation, I don't care, right? The solar salt is not bothered by a sudden decrease because a cloud passes by the system, or because of vibrations temporarily defocusing some of the mirrors. Whereas in a system with a heat exchanger on top of a tower, those rapid fluctuations in the thermal intensity on the heat exchanger's surfaces cause severe metal fatigue and often result in failure of the heat exchangers. The other advantage of this system is that I have this big vat full of hot salt. I can use that salt to make electricity whenever I want, right? So now I have dispatchable solar electricity, right? Which is going to be increasingly important as the penetration of solar energy in the global energy mix increases, right? I think a fact that many people don't appreciate is that the more solar we have, the less valuable it will be in midday because you can't move traditional solar. You can't move PV from midday to later in the day unless you have a storage technology. In photovoltaic technologies, a lot of interesting work going on at MIT. It's one of the very largest areas of energy research on campus. This is an example looking at technology for the photovoltaic materials, in which materials design using either polymers with custom chromophores or using quantum dots, material can be tailored so that the PV material absorbs in the infrared region rather than in the visible region, and produces electricity and allows light to pass through the PV material. That means I could put photovoltaics on glazing on buildings, and I could increase the amount of area I have available for photovoltaics in a big city. Or, as he's done now, is to apply that to portable electronics devices, our cell phones, iPads, things like that. So the idea in these portable electronic devices is that you could make the glass on the cover out of a PV material that's transparent to visible light. So while you're using your device, it can charge from this PV material. This application is really important because that's a high value added application. You'd be willing to pay a lot more for this transparent PV material if it keeps your iPhone charged all the time than you would be willing to pay for electricity in your building from PV glazing. This video just illustrates by shining a light on this device. You can see that you produce voltage, and you saw in the video that if you cover up the surface, you don't produce power any longer. So it looks like I'm out of time. So I'm going to just skip to the end and make one last comment about one of the projects going on at MIT, which is the utility of the future. So we've looked at a number of applications where natural gas being one, which can be distributed easily. You can have gas generators. Solar PV, which is easily put on rooftops. And so increasingly we find in the world distributed generation. We find distributed storage is possible through better battery technologies. We find increasing electrification of the transportation sector. That's still in the very early stages, but it is growing. We see more interesting IT technologies brought to bear on energy, so smart meters in homes and businesses. All of that is changing the way the utility business works and is forcing a rethink of how you interface with your customers and how energy producers and energy suppliers capture rents, basically, in their business models. And so we have launched a study that we call Utility of the Future, which is aimed at innovating the business model rather than technology per se, and understanding in different regions of the world and with different regulatory regimes what might be a business model which is a successful model for a utility. So I will stop there and leave you with this quote I like from Will Rogers. I mean, I like to read this regularly because I think we do a great job at MIT in innovating and thinking out of the box. But as he points out, even if you're on the right track, you're going to get run over if you just sit there. Right? So always be on the move in this field. So thank you very much. I appreciate your attention.